In this video, we'll walk through the theory behind neural networks, so that in the second part of the lecture, you have an easier time understanding the code that implements neural networks. And so in general, we can think of neural networks as mapping some input to some output. And of course, input and output can be very complicated things, for example, mapping an image to a description, or if you think of Google Translate, mapping one language to another language. But the mappings from input to output can also be very simple. So maybe we just map some number to another number. And so the mapping or function between input and output depends on the weights or parameters of the network. And in our case here, we just have one weight connecting input and output. And so since we want to map from 1 to 2, we could say that our weight is 2. And so the input is multiplied with the weight, and that's then our output. And with this weight of 2, we could say that our network models a linear function. These input and output circles we also call neurons. So in our case here, we have one input and one output neuron. And in this example here, the neurons do not really relate to the biological counterpart. So of course, our neuron here gets some input. That's also what's happening in the brain. But then besides that, there's nothing happening. And so what we can do to improve the complexity of our model so that it can learn more than just a linear function is that we increase the number of neurons. But before we add more neurons to our network, let's check out what a neuron can do besides just outputting one value or then receiving that value with a weighting. And so the first thing we notice here is that we have multiple inputs. And these inputs are also weighted. So we have one weight here, here, and here. And so we multiply the inputs with the weight and then we sum them up. And this is now more related to the neurons in our brain, because some inputs can have an increasing or a decreasing effect to our neuron. And so we could model this with having a negative weight. And then once we have summed up all the weighted inputs, we call that the drive of the neuron. And to this drive, we apply an activation function. And maybe you've heard about threshold functions, so that a neuron only activates when it reaches a certain signal strength. So if the drive here is above a certain value, then our neuron would activate. And while things like this can work in a biological context, the problem here is that these threshold functions are not differentiable. And for us, it's really important that we can take the derivative. You'll see why in a second. And so instead of having this threshold function, we switch to this ReLU function here. And the ReLU function is one of the simplest activation functions, but it often does a very good job. And so the ReLU function is 0 for negative input values, and then for positive values, it represents the identity. So if x is 2 here, then y is also 2. And so now before we go into why we need derivatives, there is one part missing in our neuron here, and that is the bias. And so the bias, we can think of an extra input to our neuron that does not depend on the actual input coming from an image, for example. And so this bias gives the model some added freedom. And we can illustrate this by going back to our first example here, where we had a very simple neural network that modeled a linear function. And while we could model any linear function, the problem is that we cannot model an intercept. So a function that goes like this, for example, or like this. And so to achieve this offset, we can simply add a bias to our neuron. So in our case, let's say that's the value 4, then our bias would be 4. Okay, so now we know what a neuron can do. So let's add more of them to our network. And we can add more neurons either by increasing the number of layers that we have. So here we have one more hidden layer. And we say hidden layer not because we cannot see the values in these neurons, but because often we're not interested in them. So mainly we're interested in the input and output, so input and output layer. And what happens in between is of course very important, but not really interesting for us. And so let's quickly walk through how we go from input to output. So we start here with some input, and in our case, we just have 2 values. But of course, we could also have 100 values that correspond maybe to a 10 by 10 image. And so every input is then passed to all the neurons in the next layer. So the first input goes here, here, and here, and the second input goes here, here, and here. And all of these connections are weighted. So each neuron is connected to the previous neurons. So the input here, their values are weighted and then summed. And then after summing them, we apply the activation function. And then again, once we have computed the activation for all the neurons here, the values go to our output neuron, where again, the values are summed up, or weighted, and then some activation function is applied. And this value is then the output of our network, which we also call y hat. And so this is the prediction of our neural network. And of course, we shouldn't forget the bias. This is also added for every neuron. And so because every neuron in this layer is connected to every neuron in the previous layer, we also call this layer here a dense layer, so because it's densely connected. And now when we then have our output, so the prediction of our network, we can compare it to the target, so the actual value. So let's say our input was some image, maybe of either a cat and a dog, and then the output here would either be cat or dog, so maybe we present it as either 0 or 1, and then we compare this 0 or 1 to the actual target. And by comparing prediction and target, we can calculate a loss. And the loss tells us how far the model is off from predicting the correct target. And there are a lot of loss functions, for example, mean squared error or categorical cross entropy. And so we could also have a very simple loss function, which could be just y hat minus y, and then the absolute of that. And now, for example, if we say cat corresponds to 1 and dog to 0, then maybe our model predicts a cat, but actually the image is a dog. So we have 1 minus 0, which then corresponds to 1. And so you'd have a loss of 1. The same thing happens if our model predicts a dog, but actually our image is a cat, so then we have 0 minus 1. The absolute of that is also again 1. And so for the cases where y hat and y don't match up, we have a high loss. But if they do align, we have a loss of 0. And so our goal, or the goal of the network, will be to minimize this loss. Of course, not just for one image, but for all images. And this is not a central question, so how can we reduce this loss? And so to reduce this loss, we'll do gradient descent. But before, it should be clear what the loss depends on. And so what the loss depends on are the input and the model's parameters, so the biases and weights. And since the input is fixed, we have to ask how can we change the model's parameters such that the loss is minimized or decreased. And we can answer this with gradient descent. So we can think of the loss as a function of our weights. And in this case, we have just one weight, and this gives us then this graph here. And if you now think back to your math classes, you might say, okay, this is very easy. We just calculate the minimum of the function, and that gives us then the optimal weight. And this, of course, works very well in the one-dimensional case. But the problem is that we don't just have one weight, but sometimes up to 1 million. And taking the derivative of a function with 1 million parameters is basically impossible. And so we need some other solution, and this solution is gradient descent. So let's say we pick a random weight, maybe in here, and this weight corresponds then to this loss here. And while it's impossible to take a derivative with respect to 1 million parameters, what we can do is take partial derivatives for a single point. So we're asking what is the slope at one point in our function. And in this case here, the partial derivative would be positive. So as our weight increases, so does the loss function. And so what we now do is that we subtract this gradient from our weight. So we're descending along the gradient. So let's say the gradient at this point is 2, so we have a slope of 2. So 1 in this direction, 2 up. Then we would subtract 2 from our weight, which brings us to here. We can imagine the same in this position here. Here we have a negative gradient, and so we add that to our weight. So we go from here, this position, to maybe here. That brings us to here. And then here we have this gradient, which brings us here. And so with this method, we're guaranteed to land in a local minima. It's important to note that it doesn't guarantee us to land in a global minima. So if we start here, we will end up here, but not in here. And this gradient descent can be even more intuitive if we go to 2 dimensions. So here we have 2 parameters or 2 weights. And if we start maybe up here, then we can think of it like a ball that rolls down to the local minimum. And just to make it clear, it's possible to calculate the gradient for one point for this function that has maybe 1 million parameters, but solving the whole derivative, so the derivative for every point, such that we then calculate every minima, that is not possible. So we always calculate one gradient and then move in that direction, or the opposite direction. Okay, so now a short summary from the start. We start by giving our network some input, maybe an image. Then this image goes through our layers, through our neurons, until we get an output. Then this output is compared to the true label, which gives us then a loss. And then we ask, how does this loss change based on the model's parameters? And this gives us then the gradient, through which we then change our weights. And so after then changing our weights, we can pass in a second image, we get another loss, another gradient, and we can repeat that for the whole data set and even multiple times. And so through every image, our network learns and is adapting its weights or parameters.